So today in our video, what we're going to take a look at is the very end of the chapter, and we're looking today at phase changes, as I just wrote all over my screen. Well, that's okay, we can ignore that, right? But as we look at phase changes, what we're going to take a look at are some of the ways that they happen, what kind of energy changes are involved, and then we're especially going to look a little bit at something called a phase diagram. So let's kind of jump right into that. And basically, the first thing we see here is we have a little slide that's going to show all of our different phase changes that we can have. We have starting off from a solid phase, well, at least the three phases we worry about as chemists. Going to the liquid phase, which would be melting. Going to the gaseous phase, which would be vaporization. And we'll look at that a couple different things too, because we'll also look at something called evaporation here, and we'll see how that's a little bit different from vaporization, what's going on a little bit differently. And we'll kind of review a little bit too one particular term here, something called a vapor. And going the other way, you have gases. Going to liquids is condensation, going to liquids to solids is freezing. And then you have sublimation and deposition, which is that direct change from a solid to a gas or a gas to a solid. Now, one thing that's important to realize in all of these different phase changes is that energy is required somehow. Some type of energy change will always occur to make them happen, depending on whether energy is being absorbed to make it happen or energy is being released to make it happen. And that's kind of our next slide that we're going to take a look at what's going on in that case. And so first of all, before we get to the changes of energies happening here, we want to take a brief look at something called energy distribution in liquids. So we'll have a couple of little graphs that we're going to take a look at. And basically, as we look at this first graph, what we're seeing is liquid at two different temperatures. And the curve is showing us the fraction of molecules, what kind of energy they have. So if this is T1, the blue line is T1, that means that most of your molecules are going to have this average kinetic energy at this high point right here. But you notice that as we go away from that curve, we have less and less particles that have energies that are spread out. But they do have more energy, and those particles have less energy. And why is that? Why do particles have more and less energy in the liquid when it's at a temperature? It's because of those collisions. Energy is being transferred back and forth between your particles. So obviously, some particles are picking up kinetic energy. Some particles are losing kinetic energy. So the lower your temperature is, the higher this bell curve is, the higher the number of molecules is that will have a given temperature. As you heat something up, notice what happens. That curve is lower, but it's more spread out. More particles have a bigger range, even though most of our particles are still going to have that high point with that particular energy. Now, as we look out here, what's happening, we have these particles down here, which are lower energy, they're moving slower. The particles up at this end are moving faster. There is a point here where this E line is. That's called our escape energy. Particles above that temperature have enough kinetic energy that they can escape the liquid. They can break the attractive forces holding them together, those hydrogen bonding forces, the dipole-dipole interactions, the van der Waals forces, and they can go into that liquid phase. Now, what's happening in this case, too, is basically at this point in time, we're assuming this isn't the boiling point. So what we have happening is evaporation. And evaporation, we'll see again, I mentioned we'll talk about it again, but it's going to come up again here shortly, where we'll see what the difference is between that and vaporization overall. But that's kind of showing what's happening, is if we went to a higher temperature, our curve would be even broader, and actually this curve would be higher up over here too, to show where that escape energy is, how many particles have that ability to escape. The higher the temperature is, the more particles have enough energy to go into that vapor phase. And again, remember, a vapor very simply means it's a substance that's normally a liquid at room temperature that has enough energy that it can change to the gaseous phase. So things that have a strong odor to them, like gasoline and perfumes, that very easily change to the gas phase, or butyric acid, on the other hand, is a bad one that we don't like to smell. Those things have high vapor energies or have high volatility. That means they change to that vapor phase very easily. Okay, now phase changes, or we look a little bit again at this case, it's showing the same things again that we just talked about. At a low temperature, only a small number of particles in your liquid have enough energy to escape. You see, this is a pretty small number of fraction of particles. So you have not much vaporization happening at that point, or evaporation. But as your temperature goes up, you have a bigger fraction of your particles. More particles can escape the liquid, and they do that. So higher temperature means you have a faster evaporation rate. That's why water in the desert doesn't last as long as water at the North Pole, because it's a lot hotter in the desert usually. Not every desert is hot, but most of the time we think about deserts as being hot. So some phase changes require energy. Energy has to be put in order to make them happen. And which ones would they be? They would be melting. Nice little snowman picture there. He's melting. It's not Frosty, thankfully. He's coming up here at Christmas time yet. We have vaporization. And in this case, this vaporization is actually talking about the boiling point. So vaporization here really means boiling. And we're changing our substance into the gaseous phase. And then sublimation also takes energy. And this would be dry ice going directly from that solid phase to the gaseous phase without having liquid in between, which is really what the biggest use for dry ice is, right? Use it for packing food, to keep food really cold, but without having that mess of water melting all over the place from ice. So it helps on transportation and keeps things a little bit nicer. We also have those then that are going to or actually, here's where we're talking about evaporation and evaporation, the differences. Basically, the difference is that evaporation is only going to happen at the surface of your liquid. It can only happen right there. It can't happen anyplace else. Only particles of the liquid that are at the surface can gain that kinetic energy to be able to escape. Okay, so it only occurs right there, and it only occurs below the boiling point. So evaporation can occur at any temperature, from basically 0 degrees Celsius up to the boiling point, but not counting the boiling point. Vaporization, on the other hand, is when water is turning into a gas, any place inside the liquid is able to form a gas bubble, which then goes all the way to the surface and then can escape. And that occurs when the vapor pressure of your liquid is equal to the atmospheric pressure. And basically at sea level, we know that then that vapor pressure would be 760 millimeters of mercury, or your standard atmospheric pressure. But that changes based on elevation, changes on the pressure of the day. But when boiling will occur, when the pressure inside the bubble is equal to that atmospheric pressure pushing down on the container. That's boiling. Okay, so vaporization is really what we think about as boiling. Evaporation is, and it occurs throughout the liquid. Evaporation is occurring just at the surface of the liquid, and is much, much slower process. Okay, so that takes us then to those phase changes that release energy, and it's going to be pretty much the opposite of the ones we just talked about. So going to higher energies going that way, which would point the other way probably for you, means that you're going to a less ordered state. When you're going to a more ordered state, then you're releasing energy to get those particles to pack tighter together. So freezing, water turning to ice cubes. Condensation, you get that mist, or gaseous water or steam condenses or changes back to liquid water. And deposition, where gas, for example, water in this case would be our example we're using. Humidity in the air can go directly from the water phase or the gaseous phase directly to the solid phase to form ice without going through the liquid phase. And on those leaves, that's what you're seeing that deposition process. And that's pretty much what happens too, like with frost in your windshields. When you get up at this time of year, go outside and your car's outside and your windshield's covered in frost, that's deposition that's occurring. Okay, phase diagrams. We're getting close to the end already. This isn't going to be a really long video. You're probably saying, yay, thank you. And anyways, phase diagrams. What a phase diagram is, it's a diagram that's showing the 3 different phases that a substance can be in, solid, liquid, or gas, and what states that they're going to be at different temperatures and pressure. And we can look at what kind of changes are going to happen then given a different temperature and pressure it's given off. So we'll start off right away with this phase diagram for water on this side over here. And what you see is, here's our liquid phase. This is where a substance is liquid. This is a solid. This is where water is a liquid, and this is water is a vapor. And it's all based on what the pressure and the temperature are. So water can actually be a gas at really low temperatures, for example, 0 degrees Celsius, if your pressure is really low. And this is actually below 4.58 millimeters of mercury, another 0.0063 atmospheres, or 4.58 millimeters of mercury. Below that pressure, water has no problem existing as a gas, because it's that pressure involved along with the temperature that gives us our different states that we're going to have. So our normal freezing point is 1 atmosphere of pressure, 0 degrees Celsius. Our normal boiling point is 100 degrees Celsius, 1 atmosphere of pressure. So if we follow this curve, what's happening in this curve is we can see what change is happening at any given temperature and pressure. So it's, oh, what if I were at 50 degrees Celsius and I was at 2 atmospheres of pressure? That's what put me somewhere like this. So if I was at those conditions, water would be a liquid. If I go higher temperatures, higher pressures, we can see where we're going to be in all those different cases. So our states at temperature and pressure conditions is what is showing us. Now another thing that's kind of interesting is if we go follow right along one of these lines, if you follow right along those lines, at either of these cases, you're in equilibrium. That means if I'm at this point that I just showed right here, on the line, that I have as much water changing to liquid, melting, as I would have liquid water changing and becoming solid, freezing. So what's really going on here is we're saying that in equilibrium, we're not changing how much stuff we have. There's an equilibrium, a balance between our phase changes if you follow right on that line, or if you take any particular point on that line. Now, there's a couple of key things that we want to take a look at in here as well that you may have noticed we haven't mentioned yet. And they are the triple point and the critical point. Now, key points. So there's a diagram again, and we have this point down here listed as the triple point. What the triple point is it's a temperature and pressure at which your substance can exist in all three phases at the same time in equilibrium. For water, that happens to be 0.01 degrees Celsius and 4.58 millimeters of mercury. So that means your solid phase will be changing to your liquid phase, will be changing to your gas phase at the exact same rate that they're changing back and forth the other ones. So if you had 10 grams of solid, 10 grams of liquid, 10 grams of gas, that's always going to stay the same at that temperature. It's going to melt, it's going to freeze, it's going to condense, all at the same rate. Okay, that's what it means by triple point, where they exist at the same rate at the same time in equilibrium. The other point here is called the critical point, and that is what we call the critical temperature and pressure at that point. Critical T and P, temperature and pressure. And what that point means, it means that at that critical temperature, that's the highest possible temperature that you can have with an amount of pressure, which is the critical pressure, that you can still change from the gaseous phase to the liquid phase. If you go above that critical temperature, for example, with water here, we're talking about 373.99 degrees. If you went to 374 degrees, 374.00 degrees, no matter how much pressure you put onto that water, that gaseous water, there is so much kinetic energy that you will never be able to condense it into the liquid phase. But at 373.99 with 217.75 atmospheres of pressure, you can make water still be a liquid. Above that, you cannot. So that's our highest possible temperature and pressure. That you can liquefy a gas. Above that, you can't do it anymore. We call it the critical temperature. That's the highest temperature you can get to, and the pressure at that temperature at which you can still change the water. So if you drop below that, for example, at 100 degrees Celsius, you can have 1 atmosphere of pressure, and you can change your gaseous water into liquid. If you're below that, it's below that. But once you get to that point, that temperature, you will never ever be able to do that again. It can never have enough energy, or it has so much energy, it overcomes those attractive forces no matter how much you push them together. This slide is just going to show us a basic general thing of what's happening in this case, where melting, freezing, vaporization, condensation, sublimation, deposition happening again. It's showing you which changes are happening. So the boundary between solid and gas, yeah, that's sublimation, deposition. That would be occurring. The boundary between solid and liquid, that's your melting and freezing. Between liquid and gas, that's your condensation, vaporization. So you can't go directly from solid to gas. For if this is just a general one, it's not water. But if I'm at this temperature, that means that when I come up here and I'm at any pressure up here, if I'm at this pressure, I can't go directly from the gaseous phase, the solid phase, to the gaseous phase. I have to go through the liquid phase to get to the gaseous phase. The only place I can have sublimation occur for this substance is under the triple point, under this temperature. then I can have sublimation deposition. Otherwise, I'm going to go through all these different changes that are occurring. So that's also another thing we can realize what those lines are. The boundaries are telling us what changes can be occurring with our values, with our substances. In our last diagram here, just going to show us the difference between different substances. On the left, we have water. On the right, we have carbon dioxide. And one thing you're going to see that you're probably going to notice is most substances will look more like the carbon dioxide one, where this line between solid and liquid goes up to the right. Water is kind of different, where it goes left, or goes up as in left instead of up and to the right on that solid liquid one. But we still see the same things. We still see a triple point. You can see that temperature and pressure is much different than what water's is. Carbon dioxide at negative 57 degrees Celsius and 5 atmospheres of pressure exists in equilibrium. Mostly, you see that at any temperatures that you're going to have, it's very difficult to get liquid carbon dioxide. You have to have a pretty good pressure. You have to have high pressures to have liquid carbon dioxide. So if you're anything under an atmosphere, or probably a couple of atmospheres, you're basically always going to be seeing deposition, sublimation. You won't go through that liquid phase at all. Okay, and that's what it's useful for us to show us what kind of changes are going to be happening. Okay, that's phase changes, or at least a little bit about it. In a coming up chapter, in our thermochemistry chapters, we'll be talking about calorimetry. We'll be talking about actually measuring energies that are going into phase changes, and we'll look at some different types of graphs. But for now, that's what we're taking a look at, is what kind of changes are happening, how energy changes are going on, and what kind of changes we can see by pressures and temperatures. After this little video in Canvas, there's another small YouTube video that's 3 minutes 51 seconds long or so, that's showing a few more things about phase diagrams in this case, and showing more animation stuff. That you'll want to watch that too before you go to class on Thursday. All right, we'll see you in class tomorrow, and watch these 2 videos.